What next?
So
Yes.
like the integer version basically of this problem, like number 37 from on page 95.
Right, the integer version is probably simpler.
Is there a way to ask that question in, like, I don't know, amongst the reals or something like that? Or would it just be,
No, you wouldn't ask it that way, because once you move into something with multiplicative inverses, everything is a multiple of everything else, so you wouldn't have concept of irreducibles.
so like,
Right, I mean, so the whole idea of factoring means factoring into irreducibles, and when you're looking at rational numbers or real numbers, everything is a multiple of everything else, so you really don't have irreducibles. Now, what I said in the context of moving from the integers into the rationals or the reals and the complexes is true, because once everything becomes invertible, it's a different game. But if you looked at the integers, which we're not going to do, but I mean, but if you looked at the integers as living inside the set of Gaussian integers, which is everything in the form an integer plus an integer times I, then inside of here, because I think this is sort of where your question is, if you know, when we looked at polynomials, things that used to be irreducible can become reducible, and things that used to be irreducible become reducible, and in fact can reduce even more. So, I mean, I think your question was in the integers, if you go to something bigger, can things become reducible that didn't used to be? Well, in the sense of the integer living inside the rationals, the reals, the complexes, the question doesn't really make sense there, because everything has a multiplicative inverse. But if you look at the integers as being inside here, then if you look at the number, so I'm going off on a bit of a tangent, so I don't want to spend too much time on it. If you look at the number 10, it's 2 to the first times 5 to the first. So the number of divisors of 10 in the integers is 2 times 2, or 4. If you look at this in Zi, the integers 2 factors into 1 plus I and 1 minus I, and 5 factors into 1 plus 2I and 1 minus 2I, and then suddenly you can say the number of factors is 2 times 2 times 2 times 2. So there are ways where you can go from the integers into something bigger where things factor. But I don't think that's really what your question was. But I didn't want to give this unequivocal, no, if you go to anything bigger than the integers, you can't suddenly become reducible. So you can, but it has to be sort of the right type of thing. In particular, you don't want too many things to have inverses. And here everything has inverses. Questions? The new version of the book will have a section about these, but the existing one doesn't. Other questions? Anyone? Yes.
The problem where we have to show that something is rational, I'm not completely understanding like the last statement in like the reason for the last statement. So like something with a raised to 1 over n equals to c over d. Like it's like a corollary on 89.
Mhm.
So that last statement where it says, so one I can like raise both powers to n,
Right.
and then so c over d gets like c to the n over d to the n,
Mhm.
and then so that's a times d to the n equals c to the n. So why does that last statement show that it is rational?
Okay. Okay, so we're talking about the proof of, so here's what we're trying to prove. So, if a and n are positive integers, then a to the 1 over n is either an integer or is not rational. So I think that's what we wanted to prove there. And the way that we prove it is, well, if you think about what it means, that a to the 1 over n is either an integer or is not rational, what that means is, if it were rational, it would have to be an integer. Because that's the meaning of the statement. So if this is either an integer or is not rational, is the same thing as saying, if this turned out to be rational, then it would have to be an integer. So what we're going to prove is, if a to the 1 over n is rational, then it is an integer. So the proof is, we're assuming it's rational. I mean, I won't write down all the details because they're there just to kind of highlight the ideas. So if it's rational, we can write it as a fraction of integers. Since this is, you start with a positive number and you're taking a square root or a cube root or a fourth root or a fifth root or something, you're going to get a positive number. So that means if this were rational, you can write it as a quotient of positive integers. I don't have to worry about any negatives coming up. And also, if I can write this as a positive number divided by a positive number, I can always write it in lowest terms. So if this were rational, I can write it as a quotient of two positive numbers that are relatively prime. Well, as you pointed out, raise both sides to the nth power, multiply both sides by d to the n, and now, here's the story about d. D is 1, or d isn't 1. That seems so simple and logical, it's not clear how it helps us. If d is equal to 1, we win. In fact, that's what we want. Because we want to show that if this turned out to be rational, then it actually turned out to be a whole number. Well, if you write a rational number in lowest terms, the only time it's a whole number is if the denominator is 1. So we want d to be equal to 1. So let's see if there's a problem otherwise. Well, if d is not equal to 1, well, if d is not 1, then it's a positive integer that's bigger than 1. Well, every positive integer bigger than 1 is divisible by some prime, because everything bigger than 1 is a product of primes. So there exists a prime p such that p divides d. So let's take a look at this. if you take the prime factorization of the left-hand side, p is going to occur. Because when you take the prime factorization of d, this prime p occurs. You raise it to the nth power, so it's raised to maybe even a bigger power here. And when you multiply by the various primes in A, maybe the exponent of p goes up, maybe not. But the point is, the exponent of p here is a positive integer. That means when you look at the prime factorization of c to the n, p occurs. So this means p appears in prime factorization of c to the n. But if you think about the difference between c and c to the n, if you know the prime factorization for c, then the prime factorization for c to the n is you don't get any new primes, it's just that the exponents grow. So if n was equal to 10, that would mean all the primes in the factorization of c have exponents 10 times bigger. Well, if n was equal to 10, every prime here, its exponent is 10 times bigger than it was in the factorization of c. But no new primes appear. So if p appears in the prime factorization of c, that means p appears, if p appears in the prime factorization of c to the n, then p appears in the prime factorization of c. But that means this prime p divided both c and d. So if there was a prime that went into d, it would also have to go into c. But you can't have a prime that goes into c and d because we said we can assume that c and d are relatively prime. So this route, d is not equal to 1, means that there's a prime that goes into d, but that same prime goes into c. That means c and d are not relatively prime. This one can't happen. So in fact, a to the 1 over n is just the integer c. So the uniqueness of prime factorization tells us that if a to the 1 over n was a rational number, then it was actually a whole number. Now, here's the good news and the bad news. If you're going to prove that a specific number on the test is not rational, I don't want you to quote the theorem and just say, it's true from corollary 3.12. I'll actually want you to come up with an argument for a specific number. So, I mean, I might ask you to prove specifically that 244 to the 2/3 is not rational. So I might ask you to do something like that sort of from scratch. Well, I'll actually, on the exam, get you started. But in other words, and this is sort of from Lauren's question way back when about proofs, I mean, I would like people to be able to do proofs of this form, but I mean, the good thing is there's kind of a template for it, and it doesn't require a whole lot of originality. I mean, you have to understand the ideas, but you can sort of follow the template. And I'm guessing somebody probably wants me to do this one. Okay, so let's prove that 244 to the 2/3 power is not rational. So, again, proofs should have a certain amount of originality, but it's kind of unfair to expect too much originality on a timed exam. So there's a certain template. Almost all the times that you're asked to prove that something is not rational, and this is probably what you did 660, you'll say, suppose it was rational, then I can write it as a fraction. And typically you'd say there's no harm in saying, and I can write it as a fraction in lowest terms, then you just sort of do the algebra with the equation you get and see if something crazy happens. In particular, in our case, does something come up that contradicts the uniqueness of prime factorization? So these things tend to start out, suppose not, then 244 to the 2/3 is rational, and we can write 244 to the 2/3 equals, say, C over D, meaning we can write as a fraction. But if you take 244, take the cube root, and then square it, that's a positive number. So if you can write this as a fraction, it's a positive fraction, so I can assume that both numerator and denominator are positive integers, and I can assume that they're relatively prime. So it's rational, and we can write this as a fraction where C and D are positive integers, and the greatest common divisor is 1. So what we have to do is somehow turn this into an equation involving prime factorization. And the point is, even if you don't know the exact prime factorization, you can still probably maneuver this to get a contradiction. So, if we're comparing prime factorizations, we need to look at prime factorizations of integers. We don't want fractional exponents, we don't want fractions, we want to write this about integers. So, first thing I want to do is cube both sides. Next thing I want to do is get rid of fractions. And next I sort of need to write this about something having to do with prime factorization. Well, the only number that's explicitly there is 244. And 244 is obviously important because there are some numbers that if you raise them to the 2/3 are rational. Like if you raise 8 to the 2/3, it's rational. So I mean, I obviously need some properties of 244. I need its prime factorization. So what is the prime factorization of 244? Prime factorization of 244 is okay, so when you factor out 2 squared or 4, you're left with 61, which is odd, so you know there are no more 2's left. Is 61 prime? Yes. So this becomes 2 to the 4th, 61 to the 2nd, d cubed equals c cubed. This is the key equation because it uses the prime factorization of 244. Because again, you need to use the prime factorization of that specific number because there certainly are numbers like 27. 27 to the 2/3 is rational. We need something about the prime factorization of 244. Well, here's the key. We know, well, we don't know what C and D are, but we know absolutely, positively, that since there's a 2 here, right, there's a 2 to the 4th, whatever, there may or may not be 2's here, but all that would do is it would just increase the exponent of 2 on the left-hand side. When you look at the prime factorization on the left-hand side, it actually has a 2 in it. And the prime factorization on the left-hand side also must have a 61 in it. I don't know exactly what the prime factorization of this side looks like. But it has to have a 2 in it. The exponent of 2 is going to be 4 plus whatever the exponent of 2 is over here. And on this side, the exponent of 61 is going to be 2 plus whatever the exponent of 61 is over here. So, staring at this absolutely positively 2 and 61 are primes on the left-hand side. Therefore, they must be primes that go into the right-hand side. Now, I only need one contradiction. So I can clean this up later. At the moment, I'm not quite sure which contradiction I'm going to come up with, but at the moment I know that 2 and 61 must be prime divisors of, because again, uniqueness of prime factorization says any primes that occur here have to occur here. So 2 and 61 must be prime divisors of C cubed. But whatever the prime divisors of C are, when you cube it, you don't get any new primes. You just up the exponents. So 2 and 61 must be prime divisors of C cubed and of C. Now, so I know that, again, I don't know what C and D are, but that's going to be okay. 2 and 61 have to occur in the prime factorization of C. So let me look at the exponent of 2 on both sides. I'll write things down at the end. If I look at the exponent of 2 on the right-hand side, C contains 2 to some power, right? But when you cube it, 2 is raised to what power on the right-hand side? I don't know what it is, but it has to be a multiple of 3. Again, C is 2 to some power. C cubed is then 2 to 3 times something. So the exponent of 2 on the right-hand side must be a multiple of 3. What about on the left-hand side? I don't know what power of 2 goes into D, but when I cube it, that means the power of 2 that goes into D cubed must be a multiple of 3, which means the exponent of 2 on the left-hand side must be 4 more than a multiple of 3. Right. Can something simultaneously be a multiple of 3 and 4 more than a multiple of 3? No, so I can use that to get a contradiction. That's using the number 2. If I wanted to use the number 61, I could say on the right-hand side, the exponent of 61 and the prime factorization of the right-hand side must be a multiple of 3. But the prime factorization of the left-hand side has 61 to a power of 2 more than a multiple of 3. So if I compare the exponent of 61 on both sides, on one side the exponent of 61 is a multiple of 3. On the other side the exponent of 61 is 2 more than a multiple of 3. There's no way you can simultaneously be a multiple of 3 and 2 more than a multiple of 3. So can you see that you could use either 2 or 61 to get a contradiction? Because when you compare the exponents of 2 and 61, on the right-hand side, the exponent of both 2 and 61 is a multiple of 3. On the left-hand side, the exponent of 2 is 4 more than a multiple of 3. Can't happen. Here, it's 2 more than a multiple of 3. And hopefully what you can see is, if I took some number here, when I take the prime factorization, the only thing I need to get a contradiction is some exponent not being a multiple of 3. I don't care which one, right? And I don't need both, as long as some exponent is not a multiple of 3. And that makes sense. In other words, in order to get a contradiction, I need that some exponent is not a multiple of 3. And the reason that makes sense is because if when you factored your number, if every exponent was a multiple of 3, you could take its cube root, and you'd actually get a whole number as an answer. So it's like if you looked at the number 8 or 27, all your prime exponents would be multiples of 3. You wouldn't come up with a contradiction. Well, you shouldn't, Because if you try to prove that 8 to the 2/3 is irrational, you shouldn't come up with a contradiction because it is rational. So ultimately, what causes the contradiction is some exponent is not a multiple of 3.
So even if it was like 2 to the 6th times 61 squared, we use the 61 to just prove it wrong. The
Right.
2 doesn't hurt it.
Right. Again, all you need is one exponent to not be a multiple of 3 when you take the cube roots. So it's not always the case that any prime you look at will give you a contradiction. Like if I wanted to prove that 244, if I wanted to prove that 244 to the 1/2 was irrational, the problem wouldn't be, here's 244, the problem wouldn't be with the 2. The problem would be with the 61, which isn't surprising because this is 2 times 61 to the 1/2. So it's only the 61 that causes the problem.
And we want
Right. I mean, we need to come up with a contradiction. If you didn't come up with a contradiction, like for this one, if all your exponents were a multiple of 3, that would mean that this number was a perfect cube, and the answer was a whole number. Now it turned out, we didn't lose anything, it turned out we actually never used that C and D were relatively prime. I mean, you could come up with different proofs using the fact that C and D are relatively prime. I mean, you could say something like, I won't write it down, but this is going to be more similar to kind of what you probably did in 660. What you might say is 61 must be a divisor of C, right? Because it's on this side. So the factorization of C must have a 61 in it. When I cube it, the factorization of the right-hand side must have at least a 61 cubed in it. So if I look at the right-hand side, the factorization of the right-hand side, 61 has to be raised to at least the 3rd power. But if I collect my 61s, since I'm looking at primes, I don't get any 61s here. I get 2 copies of 61 here. I need another copy of 61, because otherwise the exponent here is at least 3, and this is only 2. That means I have to pick up a 61 from D. So, or I have to pick up a 61 from D cubed, which means D has to have a 61, meaning 61 would be a factor of both C and D. Contradiction. And that's more the type of argument that you did in 660, like the square root of 2. Because at that point, you didn't have the uniqueness of prime factorization as a tool. Other questions on this? Again, I've lost track of how long this one is going, so let me save this one.